Hi guys, welcome to another video in the ICD1 video series. In this video, we'll be looking at the OSI model, the TCP/IP model, and how they relate to network communication. Okay, so what are these models? The TCP/IP model and the OSI model are two models that describe how devices in a computer network can communicate with each other. So in a previous video, we saw how we can connect devices in a computer network together, and what types of devices we can use for local communication and wide area communication. So in this case, a switch is used for local communication, connecting devices that reside within the same area together, whether that be through a wired connection or wirelessly through radio signals. And we saw that we can use a router to connect our network to the internet and essentially access any device in the world. So we have all this physical infrastructure, we have all this physical connection, but now how do we use that physical connection in order for two devices to be able to communicate together? That's where these models come into play. These models define a set of rules that any device can follow, no matter their vendor or manufacturer, which defines protocols and guidelines that devices can use in order for them to use the physical infrastructure to be able to communicate. Now both these models are very similar, and we'll actually see the different layers of these models in the next few slides. And so the way it works is that as these models are split up into different layers, and as a device moves through these layers, we're adding more information to the data in order for that data to be able to be successfully sent to the destination device. This is known as creating a packet. So you can think of a packet is just data which is encapsulated in additional what we call headers, in order for us to add more information so that data can be successfully sent to the correct destination device. So the OSI model is split up into 7 layers, and each layer provides some sort of function in network communication, and each layer provides a service to the layer above it. So as an example, the Datalink layer defines how two devices in the same network can communicate, but it's the physical layer which puts that data onto the wire and actually sends that data. Or as another example is the network layer that defines the end-to-end communication. So where this data is coming from and where it's going to. But it's the Datalink layer which defines the next device in line that we can use to eventually reach that destination device. So each layer provides a service to the layer above it. And so with the OSI model, layer 1 is the physical layer, layer 2 is data link, layer 3 is network, layer 4 is transport, layer 5 session, layer 6 presentation, and layer 7 application. There's quite a lot of layers to memorize. So a mnemonic you can use is please do not throw a sausage pizza away. So please, physical, do, data link, not, network, throw, transport, sausage, session, pizza, presentation, away, application. A little mnemonic that you can use to memorize the OSI model. The TCP/IP model is essentially the same as the OSI model, but layers 5, 6, and 7 of the OSI model have been combined to one layer in the TCP/IP model. So layer 1 is physical, layer 2 is data link, layer 3 is network, layer 4 is transport, and layer 5 is application. The network in the original TCP/IP model, the network, physical, and data link were combined into one layer called network access. When the TCP/IP model was updated, the network access layer was split up into the data link and physical layers, giving us 5 layers. So original, it was 4 layers. The updated version is now 5 layers. So now what's the difference between the OSI model and the TCP/IP model? Well, the OSI model is used more as a reference model. So the OSI model was an attempt to standardize network communication no matter what kind of network we used. Back when the OSI model and TCP/IP model came out, most of our networks were TCP/IP based. Nowadays, our networks still use the TCP/IP protocols. So because of that, the TCP/IP model won, because it was the actual model created to define how devices in a TCP/IP network can communicate and share information. And also the TCP/IP model, each layer maps to better maps to a stage of network communication, better than the OSI model. As an example, the OSI model defines a session layer, which rarely isn't used in real network communication. The session layer says that we establish a session. Well, that's done through the transport layer, it's not done through the session layer itself. And so that's why the TCP IP model won. But the OSI model is used more as a reference model and for learning. Because the OSI model goes in more detail, it allows you to better understand how network communication works, and essentially allows you to better understand the TCP IP model as well. Like I said before, OSI model tried to define how devices on any network could communicate. So whether it be IP-based networks or IPX or so on and so forth. But it tried to standardize communication. TCP IP model just said, this is how devices in IP or IP version 6 networks can communicate. That's the wrong slide. Okay, so what I'm going to do now, I'm going to go through the different layers of the OSI model and talk about how the functions performed at each layer and how it relates to network communication. And the reason I'm going through the OSI model, like I said before, is used as a reference model. Once you understand the OSI model, you'll understand the TCP IP model as well. So layer 7 is the application layer. The application layer defines protocols that software applications can use to interact with network devices. So it's essentially a set of rules defining how software applications can interact with network devices. So when we have our software developers making things like web browsers and file transfer applications, they don't have to be concerned with how those applications are going to interact with a web server or with a file server. There's already protocols and rules which define how those applications can interact. So as an example, HTTP is a protocol that defines how a web browser can pull a web page from a web server, or FTP defines how a file transfer application can upload a file to a file server or download a file from a file server, or DNS defines how a computer can resolve a host name into its IP address. The presentation layer just ensures that the data we're going to send to the destination device is readable by the application at the destination device. Remember, when two devices are communicating, normally that data is traveling from an application on one device to an application on another device. So we have to ensure that when the data gets to the application on the destination device, the application can actually read the data and can actually understand it. So at the presentation layer, we're talking about trying to reformat the data and restructure it so that the application can read it. As an example, we could be converting an EBCDIC file to an ASCII file. The presentation layer also handles data compression and encryption. It's kind of like how we can translate from one language into another language so that we can understand. What the actual source material meant. It's the same thing with the presentation layer. We're trying to convert it into a format so that the application can understand it. Now at the session layer, it takes care of establishing a connection between the two devices and managing that connection and also terminating that connection. Like I said before, this is normally performed at the transport layer in real networks. Examples of protocols that layer up named pipes and NetBIOS. And at the session layer, we can determine whether over that connection both devices can send and receive at the same time, whether only one device can send or whether whether only data can be sent in one direction. It also deals with how to restart the connection as well. Transport layer. So the transport layer defines that data is sent between two devices, either reliably or unreliably. So TCP defines that we send data in a reliable manner, which means that as data goes between two devices, a connection is set up between the two devices, and any data that, let's say, PCA sends to PCB, PCB will acknowledge receipt of that data. Say, okay, I received that data. Any data that is dropped is resent by PCA. So why would we want to use an unreliable protocol? Well, the problem with TCP is that by establishing a connection and by providing all the kind of features it provides, which we will look at in another video, such as error detection, resending of frames, acknowledgement, it adds a lot of additional data, additional information to the data, which makes data transfer slower. Now, in certain applications like voice, video streaming, the speed that we send data at is essential, because when we're video streaming, we want to send data. We want to be able to send and receive data as fast as possible, so that we can keep the video stream as smooth as possible. With UDP, because it's got such less features, the amount of information it adds to the data is a lot less, which means that there's less overhead, which means that it takes a shorter time for us to build the packet and actually send this packet to the destination device. So that's why UDP is used for real-time applications, because data can be sent much faster, which results in less latency, time it takes a packet to move from one device to another device. So the transport layer handles segmentation, which is essentially taking data they receive and segmenting it into manageable chunks that the destination device can understand and can handle. It also deals with traffic control, making sure that the destination device isn't overloaded with too much data. Transport layer also deals with port numbers. So a port number defines what application the data is meant for on the destination device. So essentially, let's say we're trying to send data to this web server. Now this server is not only a web server, it's a HTML server, a DNS server, FTP server, could be a DNS server and a DHCP server, but it's also a web server as well. When the data gets to this destination device, how does this server know that this data is meant for the web server application on it and not the FTP server or the DNS server? It looks at the port number. The port number defines the application on the device that the data is meant for. So in this case, HTTP uses the port number of 80. So by defining a port number of 80, we're saying that this data is meant for the web server application on this device, which ensures correct delivery. So with the transport layer, we'll also define a source and destination port number. So the source port number will define the application on the sending device that sends this data. So then now when the server responds back, it ensures that this data goes back to the correct application. And we can have multiple applications running, and each application is given a different port number to identify each application individually. So by defining a source port number, it ensures that the data is sent back to the correct application on the device. Now we move on to the network layer. The network layer defines how two devices can communicate end to end. So network layer allows two devices in different networks the ability to communicate. So imagine that these two devices are in different networks. The network layer says that devices in two different networks are able to communicate by using IP. IP defines logical addressing. With logical addressing, it allows us to group device. It allows us to assign devices to different groups, which makes our networks more efficient. When we look at IP, we'll see how by grouping devices together into logical groups, we can make our networks more efficient and make sending data and handling data more efficient as well. The good thing with IP, because it's all logical addressing, it means that we can change the network our devices connect to. Now with the network layer, it makes sure the packet is sent to the correct device, and like I said before, it defines who we're sending it to end, allows us to communicate with devices in different networks. When we move to the next slide, we'll see how this actually functions and interacts properly with the data link layer. So the data link layer defines who we're going to defines how two devices in the same network can communicate. It essentially defines protocols like Ethernet, PPP, and HDLC. So what that means is that let me draw a sample network. Okay, we have a switch to a router, to another router, to a switch, to a device. Now with the network layer, let's assign these devices an IP address. So 2.2.2.2. The network layer will say that this packet is going from 1.1.1.1 and being sent to 2.2.2.2. The data is going from 1.1.1.1 to 2.2.2.2. So this is saying that we want to send this data, and we want this data to eventually end up at 2.2.2.2. But the data link layer defines how we actually get there. So the data link layer says that for host A to reach PCB, host B has to use its router in order to reach that device. and this router has to use this device. So it defines, the data link layer defines from a local area perspective, from each device's perspective, the next device to use in order to reach the final target destination, the final destination. So network layer, end to end. This is where it's going from, this is where it's going to end to end finally. Datalink layer, this is the device that I'm going to use in order to get one step closer to reaching that. So in this case, the host will use this router to get one step closer to reaching this, and the main goal is to eventually get the data to this destination device. This router is going to use this router to go one step closer, and this router can send this data directly to the target destination device. So just to recap, network layer, end-to-end communication, allows two devices on different networks to be able to communicate. Datalink layer allows two devices on the same network to communicate, and allows us to get one step closer to the destination device when the destination device resides on a different network, because the datalink layer defines where to send the packet next from each device's perspective in order to get to the final destination. So now we move into the physical layer. The physical layer is responsible for actually putting the data on the link in order for it to be transmitted to the next device in line. For putting voltages and bits and zeros and ones on the cable. And physical is defined as anything that you can touch. So we've got physical cable rates, Ethernet cables, wireless radio frequencies, so on and so forth. So in this video, we've talked about the different layers of the OSI model and the TCP IP model as well. We've talked about each layer and what each layer does. Now in the next video, we're going to tie all of this together. I'm going to go through an example in real time of how a device would use the TCP IP model in order to communicate with a destination device. I hope this has been informative for you, and I would like to thank you for viewing.